So this chapter is about stereochemistry, which is a very fundamental thing about organics. Let's start first. Stereo in anything means two of, a left-handedness and a right-handedness, like you have a stereo in which you have a left speaker and a right speaker. In organic chemistry, we would say any carbon that has 4 different groups will have what is called chirality and will have a stereo center. So we'll talk about that also. And what is chirality? It is a mirror image of a compound that will not superimpose on each other. Okay, so for example, here is a molecule and you take the mirror image of that. So COH is on the right hand side, H is here, CH3, which is going back, is still going back there, and then of course you have the CH2, the ethyl group over here. When you take molecule number 2 out of the plane of the mirror and try to superimpose on the first molecule, it will not do it. Okay, and that is what is called chirality. Okay, so again, what is chirality? Chirality is when you have a mirror image, okay, that is non-superimposable on each other. And you see chirality when we have a tetrahedral carbon that has 4 different groups attached to it. That kind of a carbon is called the chiral center. Now see, it says here tetrahedral carbon, that means it has 4 single bonds, which means that carbon here is sp3 hybridized. The mirror images of these compounds are called enantiomers. Now remember, these are mirror images, which means that the compound is the same. Okay, it's just like you looking into a mirror. What would you call yourself? You'd be an enantiomer. Okay, and so the mirror image is an enantiomer. It's a very specific name. And so the molecules are very much alike. Okay, there's really hardly any difference between them. The physical properties will be the same. The chemical properties will be the same. The only thing that is different about them is how these molecules rotate the plane polarized light. We will talk about this a little bit in a few minutes, because the plane polarized light is a very specific kind of light. And so the only thing that is different about these enantiomers is how they rotate this light. And the rotation is usually in equal and opposite direction, which is why chirality or chiral compounds were discovered so late, because if the rotation is equal in an opposite direction, then you really can't tell if any molecule is optically active. And if you can't say it's optically active, it means you can't tell whether you have a chiral center. So it's all related to each other. When you draw these molecules, these chiral molecules, you have to be very specific, because the only thing that is different between them is how these atoms are attached to the central carbon, because we're talking about mirror images. Okay, so which means everything is the same. The number of atoms are the same. Everything is the same. How they are arranged around the central atom is the only thing that is different, okay, about them. So you have to be very careful how you draw them. Now we will start drawing molecules in a 3D way, and when you draw them in a 3D way, you need to have dash line and wedges. Dashes mean that the bonds are behind the plane, and wedges mean they're coming out of the paper, and a plain line indicates that things are going in the plane of the paper. Okay, remember your paper is 2D, so you have to kind of figure out a way how to draw this. So this is our way, okay, of doing this, is we have wedges that is coming out of the plane, and then dash line which is going behind the plane. So these 4 molecules are exactly the same, and you can draw them any of this way and they represent the same molecule. So see that the hydrogen is going back here, hydrogen is going back here, hydrogen is going back here, and this is a true line representation where you don't show hydrogen, but because these 2 bonds are in plane and this one is coming out of the plane, hydrogen must be going behind the plane. It's kind of understood. You can draw it any way you want, which means that you can have the CH2, CH3, the ethyl group going behind, but then you'll have to rotate the whole molecule. Okay, so here, bear with me and just follow this through. Okay, so if we rotate this molecule around and we want to put the ethyl group where hydrogen is, then you take the ethyl group, put it where the hydrogen is, and the hydrogen will come out where the methyl group is, and the methyl group will rotate to where the ethyl group is. Okay, so that's how you do a complete rotation. The OH group stays where it is because you're rotating only the bottom part. Now remember, you're not allowed to break bonds, okay? So if you take the ethyl group to the back, you really need to rotate the whole molecule. So which means that the methyl group will come to the ethyl group place and the hydrogen will come out, okay? So anyhow, that is how you represent 3D structures. Here is another one, okay, and this is for the enantiomers, okay. So here we have the OH group coming out of the plane, but in the mirror image, it will be going behind the plane, okay. I'll show you some models in class also. Here are some other enantiomers, and again, keep the mirror right over here. So here is butane, okay, in the plane. The Cl is coming out, hydrogen is going behind. Here again, so the Cl is coming out, hydrogen is going behind the plane. So if you wanted to see if these two will superimpose or not, you will actually have to literally pick this molecule out of the mirror and then try and superimpose it on it, okay. Here is the one for a cyclic compound, okay. These are mirror images of each other. Just because this is coming out doesn't mean this has to go back. This also will be coming out, except that it's in a mirror, okay, that's all. So here is an example you should work on. Without looking at this, you should find how many chiral centers this molecule has. And essentially, when you do this, you have to look at carbon that has 4 different groups on it, okay. This is a very typical kind of an exercise when you're starting to do stereochemistry, okay, is to identify whether you have any chiral centers or not. So for example, over here, this does not have a chiral center because this is not a tetrahedral carbon. So let's go to the left. This is a chiral center because you have 4 different groups attached to it, a methyl group, a ketone group, and then a CH that is attached to an OH, and then the 4th group is hydrogen, okay. And so you go on 1 carbon at a time, and in this molecule it happens to have very many chiral centers because it's just a huge molecule, okay. And so, and it has a variety of groups on it, so each carbon pretty much is a chiral carbon. The exercise for this one is for you to realize that double bonds don't have chiral centers, and then neither does this oxygen over here. But this carbon, this one, this carbon, all of these are chiral centers. So here is the answer over here. All these ones that are starred, and that is how you represent chiral center, is by drawing a star on it, is a chiral center. The history of chirality is very interesting. Louis Pasteur was the first one to discover stereochemistry, and he was actually a kind of a consultant for a wine company, and so the wine company was having trouble with the tartaric acid deposits on the wine bottles, and so he was called in and asked to look into this, and he got the tartaric acid and he started studying them, and he noticed, and that's where the power of observation is really key over here, is that the tartaric acids crystallized into 2 different ways, okay. So here are the 2 different ways, and these 2 crystals are not alike, because if you take this crystal out and then try to place it on top of it, it will not place on top of it, whereas really any kind of crystal should crystallize only in one way. So what he did is very painstakingly, he separated out these 2 crystals, okay, one going in one direction, the other one going in another direction. And no, you will not have the same kind of crystallization if you were just to rotate this molecule or this crystal. No, it will not happen. So you can get that thought out of your mind. It's not going to happen. So these 2 crystals, he separated them out, and then he observed them under his polarimeter, and he found out that they rotated the light in different directions. Everything else about the 2 crystals was the same, which means their melting point and other properties, they were all the same. And so that's when he coined this term about stereochemistry and about enantiomers and so on. But it's really a very critical discovery as far as organic chemistry is concerned, because now we figured out that there are so many chiral centers and there's so many chiral compounds in nature and otherwise. So this is the structure of tartaric acid, and here is the chiral center, and here is another chiral center. So it has actually 2 chiral centers. The sound here might be just a little bit different because I recorded this separately. But anyhow, let's talk about naming enantiomers. Now, enantiomers are mirror images of each other, which means they're exactly the same compounds, which means that you name them exactly the same way. So how do we differentiate between the two enantiomers? And this kind of a system was developed by three scientists, Kahn, Ingold, and Prelog. It's also called the Kahn, Ingold, and Prelog system, or the RNS system, RNS configuration. So that's what we do with enantiomers. So here is how we get started on this. You only have 4 groups that are attached on the chiral carbon. So if you're looking at this carbon, there are 4 groups attached to it. So which means that you look at one carbon at a time. You don't look at all the chiral centers together. Okay, so one carbon at a time then. So then you assign priorities, okay, to each of the atoms that are attached to the central carbon or to the chiral carbon. So look at only the atoms that are directly attached to the chiral carbon. So this is the carbon, which means that you will look at hydrogen, oxygen, carbon, and carbon over here. And then you assign them priorities according to their atomic weight. Okay, and so generally if you have a hydrogen, that will have the lowest priority. If you have something like oxygen, nitrogen, iodine, that will have higher priority than oxygen. So you look at the periodic table and you figure out the atomic weight from there, and then you assign priorities. So you also have to assign priorities to 4 groups only. Now the important thing over here is that you look at only one atom at a time. Okay, so this carbon that you're looking at, you should look at only hydrogen, oxygen, carbon, and carbon. So now obviously we can see a problem here, okay, which is that we have 2 carbons. So if the priority cannot be assigned based directly on attached atoms, then you look at the next layer of atoms, okay. So you have to go atom by atom. So oxygen and hydrogen, not a problem. Hydrogen is the lowest priority. Between carbon and oxygen, not a problem. Oxygen is the highest priority. So we have to decide between this methyl group here and this group over here with the carbon. So then since carbons are the same, then you look at the next set of atoms, which is the pink ones over here. So in this case, in the top one, it's hydrogen, 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 hydrogen. So that's what we have as same. And then the other carbon, it is carbon, hydrogen, hydrogen. So carbon, hydrogen, hydrogen. So which means that now the priority goes to this carbon right here because it has one atom that is higher in atomic weight. So you go layer by layer, you go atom by atom. You never look at the entire group unless you're good at it. Okay, so we'll get there eventually, but right now go atom by atom to assign priorities. So once you've assigned the priority to the groups, then you go ahead and take the lowest priority group and keep it to the back. In a tetrahedral carbon, which is sp3, this is easy to do because one of the bonds will be going back, all right? And so once that lowest priority group is in the back, you have the other 3 that are actually facing you, and the lowest group is here at the back. So when you look at these 3 groups that are facing you like a fan, then you just go ABC from the highest priority to the lowest priority group. If they happen to go right side, okay, which is a clockwise, then it's called R. If it happens to go anti-clockwise or towards the left, it is called S. R and S designations, they come from Latin words. R is for rectus, S is for sinister. So R is a clockwise, and the clockwise has to do with the priorities, okay, of the group. So highest priority group, lower, and then lowest. If it's going to the right hand side, it is considered to be a right-handed molecule, which is R. And then if it is going to the left-hand side, then that is S. Assigning the priorities to groups, as we said before also, is by atomic mass. And so here are some examples for you to go through. This one is if you're looking at an individual atom, okay, that is attached. So hydrogen, carbon, nitrogen, oxygen, sulfur, chlorine, bromine, and iodine, this is their order of priority. Hydrogen will always be the last one because it's 1, okay? And the rest of them, you have to look at the periodic table, or if you've memorized this, then you probably already know, okay? But you will have the periodic table to look at the atomic masses of all of these atoms. Remember, you're looking only at that one atom that is connected to the chiral carbon. If you cannot assign the priority looking at the first carbon or the first atom, then you have to look at the second one, okay, and what is attached to it. So the second one, in case of a methyl group, for example, is hydrogen, okay. It has 3 hydrogens attached to it. In case of an ethyl group, it will have 2 hydrogens and a carbon. In case of methylamine type group, this one, you have 2 hydrogens and a nitrogen. And in case of an alcohol, you have 2 hydrogens and an oxygen. So this is the order of priority. Again, since you're looking at the 3 atoms, the CH2, 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 these are all the same. So then it is decided by, the priority is decided by the third atom that is attached. If there are double bonds or triple bonds in the group, then there is a systematic way of opening them up, okay. And this is not that you're opening it up and removing the double bond. You're actually trying to make it easier for you so that you know how you can assign the priorities. This is the best chart that I have found so far to kind of give you an idea. So for example, if you have C double bond Y, whatever is Y will get attached to the C, whatever is on C will get attached to, or whatever is C will get attached to the Y. So the C gets the Y and the Y gets the C. Okay, if you have a triple bond, then to remove the triple bond, you need to add 2 more bonds, okay, to make it a single bond. And so now C will get the 2 Ys and the Y will get the 2 Cs. Okay, so if Y happens to be carbon, as in case of this group over here, CH2, then in that case, both of these groups are carbon and carbon. If the Y happens to be oxygen, okay, like in this case for aldehyde, then oxygen gets the carbon and carbon gets the oxygen, okay. In case of triple bond, you have YY that is attached to the C. So in this case, the C will get the CC, and then the Y will get the 2 Cs. So the Y is actually this one, will get this 2 Cs. If those was C triple bond N, then these 2 carbons here would be nitrogens, okay, and that's how you assign priority. And so if you're looking at this carbon over here, okay, and this carbon over here, so this carbon now has a hydrogen, a carbon, and a carbon attached, whereas this carbon has a hydrogen, an oxygen, and an oxygen attached, which means that this group will have a higher priority than this one. So aldehyde will have a higher priority than an alkene. Now remember again that these are going atom by atom by atom, okay, not group by group. So here are a few examples on how to assign priorities and how to determine R on S. Again, this is a very typical exam question on assigning priorities. You don't have to name anything, but you have to definitely be able to assign the priorities to the groups, okay, which means then figure out if it is going to be R or S. So here in this case, chlorine, highest priority, hydrogen is already at the back, so higher priority, lower priority, and then lowest priority, okay. So this is going anti-clockwise, and so this is S. And then looking at this one, now remember you have to keep hydrogen as the lowest priority, okay, and so this is going towards the back, which means you're looking from here. If you're looking from here, then you're looking at chlorine, and then this carbon is attached to this carbon and this one. This carbon is a double bond, so remember when you break a double bond, you will get another carbon over here, so which means that this carbon has a carbon and a hydrogen, whereas this carbon here has 2 hydrogens, so that's why it gets the third priority. The double bond gets the second priority. As time goes by, you will actually remember these things and you will not have to open these things up to find out which one has the higher priority. You will just remember, okay. So 1, 2, 3, and so this is going clockwise, and so this is R. You have to be able to do both the things, which means that if I give you a molecule, you have to be able to write RNS. And if I give you the name of a compound, you should be able to draw the RNS. Here is another one. In this case, you have 4 different groups. There is no hydrogen in here, so which means one of these groups is going to have the lowest priority. And here we have 3 carbons, 1 oxygen, which will get the highest priority automatically. And then we have 3 carbons, so 2, 3, 4. These are the 3 carbons that we have. This carbon has 3 hydrogens attached to it, So that gets the lowest priority. This carbon has 2 hydrogens and a carbon. This one has 2 hydrogens and a carbon. So which means between these two we still have to decide. But because this is a double bonded oxygen over here, this carbon will get oxygen here and will have 2 oxygens on it. So this one gets the higher priority. Okay, and so now the OH is coming out, so you keep CH3 at the back. Okay, so then 1, 2, 3, and so this is then our enantiomer. One of the tasks is also going to be whether 2 molecules are identical or not, or what is the relationship between 2 molecules. So far what you have done is, are these molecules identical, resonance structures, constitutional isomers? Now we're getting into enantiomers and so on, so now you'll have to figure that out too. So if you have 2 molecules that are given to you, I would suggest use models if you can. If you don't have models, don't worry about it. I'm going to teach you how to do this. But if you have models, it's really easy. Go ahead and build this model and this model using your model set, and then see if they superimpose. If they superimpose completely, then they're identical. If they don't, then they're not identical, obviously. So what you do then is you keep one molecule constant, and you take the other molecule and you try and rotate it in such a way that it kind of looks similar to this molecule. All right, so let's do that over here. Okay, and keeping the chlorine constant, we'll go ahead and move these groups around. Okay, and so bromine moves to hydrogen, hydrogen moves to a methyl group, and then the methyl groups comes over here. Okay, so then when the bromine is down here, remember in A over here, okay, bromine is down here, so now we have bromine down here. So again, we do another rotation and we're trying to get the CH3 back there now, okay? And so another rotation and get the CH3 back there. Once the CH3 is back there, the Cl moves here and the hydrogen will move over here. So you do a quick rotation like a fan, and this is what you end up getting. And this molecule looks exactly like A, okay? And so which means that these molecules are identical, okay? The last part here is like a cross check, okay, to make sure that these molecules are different, okay, or the same, however you want to look at it, is by switching, okay, the atoms. If you literally have to break a bond and switch it to another in order to look at the molecule and see if it's the same or not, that means that you have an enantiomer, okay? So you should not have to break any bond, okay, in order to do this. So 2 exchanges will lead it back to the same one, but if you just have the one exchange going on, that means you have an enantiomer, okay? So here what we did is we actually switched the atoms, which means you actually break the atom, break this bond, put it over here, break this bond, bring it over here, okay? This I think is a little bit more confusing than rotating, okay? Rotating a molecule is a lot easier than breaking it apart. So let's talk about what this thing is called, optical activity. We talked about the plane polarized light, and in general, polarized light goes in every direction, okay? It has no single direction, but what happens is in a plane polarized light, it actually passes through a little slit, and so you only isolate one direction of this light, okay? And that's why it's called the plane polarized light, okay? It's a restricted kind of a rotation, okay, that we have. So you have light going only in one direction, right? So when you put a molecule, okay, in the plane polarized light, it will actually rotate this light either to the right or to the left, okay? If it goes to the right, it's called dextrorotatory. If it goes to the left, it is called levorotatory, the D and the L, okay? Now this has to be small d and small l. Later on, you're going to learn about capital D and capital L, and those mean completely different things, okay? So if you see any rotation in the light, then that is because of optical activity. And remember, enantiomers will rotate the light equal in opposite direction. So dextrorotatory will be to the right and levorotatory will be to the left, okay? This instrument is called the polarimeter. The angle is measured in alpha. That's what the instrument looks like. Here is the unpolarized light. passes through the filter, and there you have this one polarized light. Okay, and here is the sample, and here is the rotation that happened. So this alpha angle then is the rotation. If it was the enantiomer, it would go to the other side. Okay, equal and opposite side. We don't have this instrument, and I don't know if you'll ever use this instrument, but that's what it is, and hopefully you will never get questioned about it either. Each molecule has its own specific rotation, okay? And so you can calculate the specific rotation when you're trying to analyze a compound and report it, okay? Because any new compound that is analyzed, you report a lot of data on it, like the melting point, boiling point, mass, and all those things. So specific rotation also has to be measured and given in case it's an optically active compound. So this is how you would calculate it. I generally don't ask you any questions about specific rotations, but this is how you would calculate it, okay? I want you to look at these two molecules over here because I'm going to explain some things here that you need to know and understand the difference in all of these numbers and letters, okay? So here's lactic acid, and these are the two enantiomers, okay, that we have. First, going through the name, the S, okay, S plus lactic acid. Then this one, the enantiomer, is R minus lactic acid. First of all, the S here stands for sinister, and that has to do with how the groups are arranged. The plus has to do with the optical rotation of the molecule, okay? And the plus can also be written as D if you wanted to, okay? Both are fine. So plus and D go hand in hand. And then of course lactic acid. And then here is the specific rotation given, and it is plus 2.6. So here is the lactic acid, which is the enantiomer now, and this is R, and this is minus. The minus can also be L, as in levorotatory, and then again lactic acid. The specific rotation is equal and opposite, okay, in direction. So minus 2.6. The plus and the minus have nothing to do with the R and the S. Please keep that in mind. Again, the D and the L, or the plus and the minus, they have nothing to do with the R and S. The R and S have to do with how these groups are arranged around the chiral center, and the plus and the minus, or the D and the L, they have to do with how the light is being rotated. Okay, so there are two different things, not to be confused. Here's another example, okay, of some molecules which have optical rotation. And again, I made it clear here, okay, there's no correlation between R and S and the pluses and minuses, okay. One term that I want you to learn from this slide here is racemic mixture. A racemic mixture is a 1-to-1 mixture of enantiomers, which means it's a 50-50 mixture of R and S, the mirror images. And so if you have a 1-to-1 mixture of enantiomers, then you don't have any optical rotation, because the optical rotation is equal and opposite. So there is no optical rotation for racemic mixtures. And so these are designated as plus minus, which means there is equal amount of both of them. Later on, we will learn something which is called enantiomeric excess. But for now, racemic mixture is an equal mixture of D and L, R or S, plus or minus. So far, we have been dealing with compounds that have only one chiral center. Now let's look at compounds that have two chiral centers. Remember, we can have compounds which can have up to 9 or 10 chiral centers. That was one of the examples that we did. So molecules can have more than one chiral center. So if you have two chiral centers, then each of those chiral centers is going to have its own pair of enantiomer. The enantiomers are mirror images. The other pair of compounds are actually called diastereomers. They have no optical relationship whatsoever, okay? Enantiomers will rotate the plane polarized in opposite direction, but diastereomers have no such relationship, okay? And so they're just called stereoisomers for that reason, but very specifically they're called diastereomers because they're coming from the same compound, but they're not mirror images, okay, of each other. The number of isomers that are formed according to the number of chiral centers is 2 to the power of n. N is the number of chiral centers that you have. So for example, If you had only one chiral center, you would have two stereoisomers, which two of them are going to be the enantiomers. If you have two chiral centers, then the number of stereoisomers you will have is 2 to the power of 2, which is 4, which is perfect because each of the chiral center is going to have its enantiomer. So you have 4 compounds. If you have 4 stereoisomers, then of course the relationship between 2 of them is going to be that of diastereomers and some of enantiomers. If you have 3 chiral centers, that's 2 times 2 times 2, and that is 8. So you have 8 compounds or 8 isomers. So it gets more and more and more. The more chiral centers you have, the more stereoisomers you have. In some cases where we have symmetry in the molecule, then that compound is not optically active. In case of one chiral center, we did not have that issue because there was not that big of a molecule to have any kind of a symmetry. Okay, but as the molecules get larger, then some kind of symmetry can be possible, and if there is symmetry in the molecule, then that compound is not optically active, which means it is called achiral. So let's look at this compound over here, okay, which has 2 chiral centers. So compounds 1 and 2. Okay, so let's look at these two first of all. And 1 and 2, these are mirror images of each other. Okay, you have 4 carbons, 1, 2, 3, 4. And in the middle 2 carbons, you have bromines, okay, attached to it. So this is one set of enantiomers. And then in the other 3 and 4 case, we have flipped one of the bromines, which means that what you did is you actually broke this bromine out, took it there, took out the hydrogen, and put it in place of the bromine. You did not do a rotation because the location of the CH3, the methyl group, did not change. So you did not rotate the molecule, okay? You actually literally broke the bond bromine from here, put it over here, and put the hydrogen over here. Once you did that, now this compound is the mirror image of number 3, okay? So 3 and 4 mirror images, 1 and 2 mirror images. So 1 and 2 enantiomers, 3 and 4 enantiomers. However, 1 and 3 are diastereomers, 2 and 4 are diastereomers, 2 and 3 are diastereomers. Okay, that's the relationship between diastereomers, which means they're not mirror images of each other, but they're still related, okay, in some ways. So diastereomers are stereoisomers of the same compound, but not mirror images. The nice thing about diastereomers is that they have different physical properties and they can be separated out. Remember, we mentioned that enantiomers have exactly the same physical properties. You can't separate them out. Okay, it's very, very tough to separate enantiomers, but diastereomers have different physical properties. So it's actually a little bit of an advantage to have diastereomers. Okay, looking at the same molecule, okay, the same one where you had 4 carbons and the 2 bromines in here. In some cases, we end up having 2 chiral centers, but not enough stereoisomers, okay? And the not enough stereoisomers meaning 2 to the power of n, as we were talking about before. So which means that a molecule that has 2 chiral centers should have 4 stereoisomers. Well, it turns out that this molecule actually has only 3 stereoisomers. And how does that come out to be? And that is because this molecule C and D, okay, they can actually be superimposed on each other. Okay, so if you take this molecule out of the plane, D, if you take D out of the plane, flip it 180 degrees, you should be able to superimpose it on C. Okay, and so that's why if it is superimposable on each other, it's not optically active, it's not chiral. These kind of compounds are called Meso compounds. So even though they have a chiral center, they still are not optically active, okay? And so they're called achiral, okay? And it doesn't mean they don't have a chiral center. They do have a chiral center, but they are not optically active. And the other way of looking at this molecule and trying to figure out if it is going to be a meso compound or not, or whether it is optically active or not, is by looking at the plane of symmetry. Okay, and so if you look at this molecule and just slices into half and just fold it on top of each other, you will see that it actually has a plane of symmetry. Okay, so each atom here, bromine is on top of bromine, hydrogen on top of hydrogen, and methyl group on top of methyl group. So it has a perfect plane of symmetry. And these kind of compounds are not optically active. Again, these are called meso compounds. Naming more than one chiral center, the process is still the same, okay, because you still have the chiral center. You still have to figure out which one is the lowest priority. But the thing is that you don't have to forget this part, okay? Don't forget this part over here. You consider this as a huge group, okay? You have to consider this also. So hydrogen here has the lowest priority for carbon number 1 here. So bromine highest priority. Then this carbon is a second priority because this carbon is attached to a carbon and a bromine and a hydrogen. This carbon is just a methyl group, okay? So this has third priority, and then hydrogen is lowest priority. So you look at this hydrogen, keep it at the back, okay? This one, keep it at the back. And then your bromine has the highest priority. Then this group over here, okay, which is over here. And then the CH3, okay? You still have the same process of keeping the lowest group at the back, okay, away from you, and keep all the other groups facing you, okay, from your eye. And so that's how you see it, okay. Then after you're done with one designation, then you look at the second carbon, okay, and now you have this hydrogen, the methyl group, bromine, and all of this. It'll have the same kind of priority in the sense that it has the same atoms, okay. And so the important thing is keeping the lowest group at the back and looking at this group as a whole, okay, and not breaking it apart, okay. And so bromine, again, highest priority, and then the CH3Br, and then finally the methyl group, okay, that's your priority. So in this case, they happen to be RR configuration. It may not always be the case, but this one is RR, okay. So the enantiomer of this is going to be SS, okay, that's what the designation will be. The diastereomer of this would be RS, okay, or SR. That would be the diastereomer. Here are some examples of diastereomers, and in this case we actually have rings also, okay, because so far we have not really quite worked with rings. So here we have 2-methyl cyclopentanol, which means that there's an alcohol group and there's a CH3 group, okay. And in case of the CH3 and the OH, you can have two relationships because they have two H's. You can have cis relationship and you can have trans, okay, relationship. So here these two are enantiomers, okay, these two groups over here, these are these two compounds, these are enantiomers. And then if you have trans, these are also enantiomers. Why are they enantiomers? These are enantiomers because they are not superimposable on each other, okay. So that is for 2-methyl cyclopentanol. And then we have the 1,2-cyclopentane in which we have two alcohol groups. The difference between this first example and the second one is that in this case, in the diol example, you have two alcohol groups, okay. In the first example, you had a methyl and an alcohol, two different groups. But here you have similar groups. So if you have similar groups, there is a chance that there's actually symmetry in the molecule. So in the cis molecule, there's actually a symmetry, internal symmetry over here. So this is only one meso compound, okay. It's not an enantiomer, it's a meso compound. The trans, however, is not superimposable, and this is a pair of enantiomers. These diastereomers that are listed over here, this is actually for each other, not between the two molecules, but the relationship between the cis and the trans 2-methyl cyclopentanol, these are diastereomers, and then the relationship here between the cis cyclopentanediol and the 1,2-cyclopentanediol, which is trans, these are diastereomers, okay. So enantiomers are mirror images, diastereomers are not mirror images. 6-membered rings, they can also be optically active depending on how the groups are arranged. One of the things that I suggest for trying to figure out if 6-membered rings are optically active or not is actually to build them, okay. Build 2 of the rings and then try and superimpose it on each other, okay, and see if they do or not. Because if they do, obviously, then they're not optically active. But if they don't superimpose on each other, then they will be enantiomers, okay. And so sometimes it's hard to look at a molecule and see if there is a plane of symmetry or not, or internal symmetry or not. In this case, it's very easy to see when you have the 1,4-dimethyl, because they're completely opposite each other. So yes, you can see the plane of symmetry in the 1,4 also. Here it's trans, you can see the plane of symmetry. It's easy to see. In some cases, it's not so easy to see. Okay, so for example, in the 1,3, it may not be that easy to see, but this one does not have a plane of symmetry. It might seem that, oh, look, you know, they can superimpose on each other. I can just flip this molecule, I can fold it, but it's not, okay. And so the cis may have a plane of symmetry, but the trans does not. So one of the best ways to do this is to actually build a molecule and then see all these rings, okay, and see if they actually superimpose on each other or not. One way of representing structures is called a Fischer projection. We learned a little bit about this in conformation analysis also. Fischer projections are very common in carbohydrate chemistry, because Fischer is the chemist who kind of developed that whole chemistry and how to write structures in carbohydrate chemistry. Structures in Fischer projections are represented as 2D structures, okay, as you see on the right here. And these structures don't really tell you what is going to the front, what's going to the back. It's kind of understood, okay? It's understood that whatever is horizontal is coming out of the plane, and whatever is vertical is going behind the plane. The middle two carbons are in the plane, all right? So the side bonds are always coming out at you, and the one on the top and the bottom are going away from you, okay? Look at only 2 carbons at a time, because if you do more than that, then you'll get confused, because for this carbon which is going behind, if it has another carbon attached to it, it will be going further behind, okay, and so that will get really confusing. So the best thing to do is look at 2 carbons at a time when you're trying to figure out what the chirality is. There are some compounds that are chiral, but they don't have any chiral centers. So here are some exceptions, okay, for those kind of molecules. The only way you can have a compound that is not chiral or does not have a chiral center but is still chiral is when the mirror image is not superimposable, okay, on each other. And the way things are not superimposable is, of course, when they're so sterically hindered that you cannot really superimpose them, okay, on each other. And so, for example, these compounds, okay, which are double bonded, remember all our carbons have been tetrahedral, which is sp3 hybridized. Here we have phenyl rings, which are actually sp2 hybridized. And so in this case, you really don't expect any kind of chirality, but it does occur because of this non-superimposability because of steric hindrance. The same thing happens for these kind of molecules, and these are called allenes. And in case of allenes, it's the same thing, okay? This bond is so stressed out that because of that, these 2 hydrogens are in one plane and these 2 hydrogens are in another plane at 90 degrees from each other, okay? And so if there were not hydrogens and some other groups, then its mirror image will not be able to superimpose, okay, on each other. And so you end up getting chiral centers. These are just examples just for your knowledge. I probably will not ask you this on the exam, but just to give you an idea. Properties of stereoisomers, we've been talking about this, so this is just a little bit of a review chart here for you, is that the enantiomers have the same chemical and physical properties. The only property that is different for enantiomers is the optical activity, okay, which is in totally opposite directions in equal and opposite direction. Diastereomers, on the other hand, they can have different physical properties. So if you have an RRSS, that would be an enantiomer, but RSSR, those would be diastereomers, okay, RR or RS, okay, that would be diastereomers. And diastereomers then would have different properties. So here we have the properties of enantiomers, okay, which is the RR and then SS. And here is the Meso compound, which is actually a diastereomer of these 2, okay, enantiomers here. So you can see that the melting point is different, density is different, solubility in water is different. And all of this is actually, in a way, it's a good thing because it helps to separate out some compounds. Otherwise, enantiomers are really very hard to separate, but because diastereomers have different properties, you can use those properties to separate, and that process is called resolution, which we will talk about. And here's resolution. Resolution is trying to separate a racemic mixture, okay, into giving you equal amount of enantiomers, because racemic mixture is a 50-50 mixture. So resolution is a technical name given to the separation of a racemic mixture very specifically. It's for stereoisomers. And what you do is you take a pair of enantiomers, convert them into diastereomers. Once you have the diastereomers, now you can separate them on the basis of physical properties. Once you have that, you've separated things out, then you convert them right back into the original compounds, okay, or the original enantiomers. So this is usually a chemical reaction that has to be done, okay. So for example, here it's a mixture of enantiomers, a racemic mixture. You react that with an enantiomerically pure compound, okay, only one, okay, R or S, just one of them. So this will then react with the enantiomers, you form RR or SR. And now because they are diastereomers, they will have different physical properties. You separate them out and then you remove the base, okay, by another chemical reaction, and this is all called resolution. A lot of these bases are actually coming from nitrogen containing compounds, and nitrogen containing compounds, amines, are very useful for resolution purposes. This whole chemistry is very important industrially and even otherwise, because as soon as you have chiral compounds, you have to have a way of resolving them, okay? Otherwise, no industry will process the drugs. If you have any drug that has a pair of enantiomers, then you have to do clinical studies on both of them, okay, to figure out which one is good, which one is bad, and what are the toxicities of both of them. So you have to study the pair of enantiomers as you would study one compound. So literally everything is doubled, okay, in case of enantiomers. Here is a nice chart, okay, of everything that we have done as far as isomers are concerned. So compounds that have the same molecular formula, okay, you can have two different kinds. You can have constitutional isomers, you can have stereoisomers. If you have just rotation going on, then you have conformation isomers, okay, and conformations we've already done before, and conformation pretty much ends over here, okay, because in conformation you can have anti and eclipsed, and then you have the two-chair conformations as far as the cyclic compounds are concerned. So that's conformational. And here when you have the same kind of molecular formula, you can have constitutional isomers or stereoisomers. Constitutional isomers are different because they are different structures. But when you have stereoisomers, then you can have two different kinds of compounds, okay, which means that something that has no chiral centers, sometimes which has chiral centers. So for example, cis and trans, this is with double bonds, okay, and so they have no chiral centers, but they're still stereo compounds, okay. They're called geometric isomers sometimes, and they can also be called diastereomers. If you have chiral compounds, or if you have chiral centers, excuse me, then you can have enantiomers, you can have meso compounds, and you can have diastereomers. So if you have only one chiral center, it's an enantiomer. If you have more than one chiral center, then it can be achiral because it is a meso compound. If it is chiral, then you have two kinds, which is a diastereomer and an enantiomer, all right? Remember, a diastereomer can also be a meso compound. It depends. So this is a nice chart to keep handy. And here's another little chart to see if your compounds are stereoisomers or not, okay? And if you have two not of the same molecules, then do they have the same molecular formula? If they don't have the same molecular formula, they're not even isomers. If they have the same molecular formula, great. Do they have the same kind of structures or not? If not, they're constitutional isomers. If yes, they have the same structure, then they're stereoisomers. Okay, then you have to see if they are cis or trans or R or S. And then if the molecules are mirror images, no, then diastereomers. If yes, then they are enantiomers. So this is a nice little chart also, flow chart, to help you figure out if you have same or different kind of molecules. I think this is probably one of the least used chart, okay, because there are easier ways of doing this. It's quite interesting to note that enantiomers can have very different properties, even though they are exactly the same structures, but just because their mirror images don't superimpose on each other, they can actually have very different properties, even though the physical properties are the same, but some properties are very different. So for example, naproxen, the S enantiomer is an anti-inflammatory agent, whereas the R is a liver toxin. And this happens in drugs sometimes, is that one enantiomer may be active, the other one may be a toxin, or one may be active and the other one is completely inactive. And that is why enantiomers have to be studied separately. Individually, the R and the S, they have to be studied independently for toxicity studies and uptake studies in order to figure out which one to use. And sometimes if the half is inactive or one of the enantiomers is inactive, it means that half of your drug is actually just wasted. So what can you do? Yeah, the drug is wasted. Okay, so what can you do? Anyhow, then there are some other properties that can be different. For example, in S-carvone and R-carvone. Okay, one has the smell of spearmint, whereas the other one has the odor of caraway. Now, I've never really smelled caraway, but I definitely know what the odor of spearmint is like. And they're quite different. Okay, that's for sure. So properties of enantiomers can be very different. Okay, and that's what makes them also very interesting to study. Amino acids are one of the common biological molecules that are optically active. There are 20 amino acids that are found in our body, and out of the 20, 19 of them have a chiral center. How do they have a chiral center? Each amino acid has one carbon that has a carboxylic acid, an amine group, and a hydrogen. The fourth group is what we call a side chain, and this side chain is what is different, okay? And that's why we have the 20 amino acids. And in the case of chirality, all 19 of them are different except in one amino acid where the R group is the same as one of the other groups, okay? And so that one of them is not chiral, but all the other ones are chiral. In our body, we find a lot of proteins, and proteins are small or long chains of amino acids. We find proteins or chains of amino acids in a variety of places. So for example, hormones can be made up of proteins, then there are enzymes that are made up of proteins, then there are transport proteins. There are different kinds of proteins, and all of them, if they're made from amino acid, it means that they all have chiral centers in them. So for example, if you take an enzyme like chymotrypsin, okay, which is a protein digesting enzyme, then it will have 251 chiral centers, okay, which means that the number of stereoisomers possible are 2 to the power of 251, okay. And so, I mean, that's a lot of isomers, okay, to think about. But anyhow, enzymes are very important in our body because they, of course, help with everything that goes on, all the digestion processes, and then the whole drug interactivity process, that is because of enzymes and proteins. And so they are actually a very important component, and chirality is very interestingly shown, okay, in biological world or in proteins because as I mentioned before, it's like a lock and key mechanism as far as the drug interaction is concerned. So if the molecule does not fit, if the key does not fit into the lock, which is the enzyme, then the drug is not. For example, here is a small molecule or a drug, whatever substrate it might be, and then here is an enzyme. So it has a very particular place to fit in, okay? And if you take an enantiomer of that, then it may not fit in, and there is no way it will fit in because the molecule, the atoms will not line up. And so this is a very important part as far as studying medicinal molecules is concerned. So when you do study medicinal chemistry, it involves making synthetically pure and enantiomerically pure compounds. Finally, here is your keywords. Okay, there are a whole bunch of keywords in this chapter, a whole new vocabulary for you. Stereoisomers, chiral centers, chirality, enantiomer. Please know all of these things. Kahn and Gold pre-log, since it's a nomenclature system, there's nothing, no keyword here, but it's a concept. So please learn the system of how to do this. The only thing that we have not really quite talked about so much here is enantiomeric excess. And enantiomeric excess is when you have more of one enantiomer than the other. And the other thing we did not talk about so much is absolute configuration. And both of these things will come up later also. Okay, so I will mention them to you in the following chapters. Absolute configuration is when you synthesize a molecule designed to have a particular configuration or a chiral center. So if you synthesize an S enantiomer or an R enantiomer, so that is an absolute configuration, so you know exactly what you're making. You're not going to end up with a mixture of the enantiomers. Okay, anyhow, so know all these terms because they're very, very specific in their meaning.